Hello everyone, welcome to this video. In this video we shall be learning about certain results which are based on Lagrange's theorem. So they are the corollaries related to this Lagrange's theorem. So what does this Lagrange's theorem tell us? It tells us that if we have some group G which is having order n, so that means this is a finite group, right? If D is a divisor of this n, then corresponding to each of this D we would have H which is a subgroup of this group G, right? So here we have first of all a notation and a name for representing and moreover one more thing is given by this Lagrange's theorem. This theorem tells us that the number of distinct left cosets, they are given by the order of G divided by the order of the subgroup, right? This thing is there with us. Now for the number of distinct left cosets of a subgroup, we have a special name and notation. The name refers to index of the subgroup H in G, right? So, and we use the notation for the index of a subgroup H in G, right? To denote this thing, we use this two straight lines, and within it we write it represents the index of this H within this group G, right? So this is the notation, and what does it tell us? It tells us that the number of distinct left cosets of subgroup, they are given by this thing, right? So the first result here tells us this thing, that according to Lagrange's theorem, this result is quite obvious. So it tells us that because by Lagrange's theorem we know the number of distinct left cosets of a subgroup in a group G is equal to the order of G divided by the order of that subgroup, and now we have used this particular notation in order to denote that. So this is the result. This is same as writing the Lagrange's theorem but changing the notion in terms of this notation, index notation, right? So this is the first result. Moving forward on to the second result, this result tells us that if we have a finite group, suppose it is given by this capital G, and we have some element which is a member of A, suppose this is a member of this group G, then the order of each such element, it will surely divide the order of the group whenever we have a finite group. So in a finite group, order of each element divides the order of the group, right? Okay, so this is the result. Moving forward on to our third result, it tells us that the group of prime orders, they are cyclic. So here let's have a look at the proof. So suppose that G is such a group where the order of this group G is prime. So let's call the order to be P, and P is some prime number, right? So we need to prove that this group G is cyclic in nature, right? So for proving this thing, what we do, we assume and take some element A from this group G such that it is not the identity element. So we will take any element from group G which is not equal to identity, right? This is our group G, we take certain element A from it. So here obviously the subgroup which is generated by this element A, taking it as the generator, its order would divide the order of G. Why? Because A is the member of G, and the cyclic group which is generated by A is a subgroup of G, and we know the order of subgroup divides the order of group. So in that case, by using this property here, we have the order of the group generated by A, it divides the order of the group G, and moreover this order is not exactly equal to 1. Why? Because in this case the element A is not equal to the identity element. If that is so, in that case the order would have to be 1. And moreover, so what we are saying this order, it divides the order of G. And what is the order of G? The order of G is some prime number, and this is not equal to 1. If that is so, that means both of them has to be equal, because there is no number between 1 and P such that it would divide P, because P is a prime number. So therefore this order has to be equal to this order which is P, right? The order of the group G. So we have this result, and moreover from here, because the order of the group G is equal to the order of the group which is generated by A, so therefore what is your G? Your G is nothing but the group which is generated by A. So that means if you write the whole of the group as generated by some member of the group, so that means that group is cyclic, and this is what we wanted to prove here. So group of prime orders, they are cyclic in nature. Moving forward on to our next result, the next result here tell us that the order of A raised to power, sorry, not the order, A raised to power the order of G is nothing but identity, right? So here for this particular result, if we suppose that what is G? G is some finite group, right? From this finite group, if we take some element A, right, then A raised to power the order of G is equal to E, right? And so this does not tell you that the order of the element A is the order of group G. No, that is not there. But obviously when you take A raised to power that number, that integer, then you, in that case you would get an identity. We are not saying that this is the least positive integer of such kind. If that is so, then that would become the order. But in this case we are not imposing a condition for the order of G to be the least such integer of such kind that when we take it to A raised to power something, we would have the identity operator. This is not the case. Okay, now if G is finite group and A is member of G, this is our result. Now let's move on to its proof. From the result 2, we have order of any element A which is a member of G, it would divide the order of G. This is sure. So therefore we may write the order of G as the order of A multiplied with some positive integer. Let's call it to be K. So we have this expression. Now, so what would be this thing? A raised to power the order of G. So A raised to power the order of G. Now substituting the value of this thing, order of G, it is equal to order of A into K. So A raised to power order of A into K. Now what is this thing? A raised to power the order of A. Whatever is the order of A, when you take it A to the power that, you would obviously get identity, because if A raised to power n is if the order of A is n, then A raised to power n is obviously identity. So this is what we are using here. So A raised to power the order of A is nothing but identity. So identity raised to power K is again identity. So therefore we have A raised to power the order of G as the identity element, and this is what we wanted to prove here in this particular result. So I hope you understood all the 4 results in this case. We have one more result which is a corollary to Lagrange's theorem. We'll be discussing that in our next video. Well, that is it for this video. Thank you for watching.